Hello and welcome back to the video lecture series for ECE 340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at autocorrelation and power spectral density. Autocorrelation is something we've already looked at a little bit. We're going to take a deeper dive and talk some more about some of the properties of autocorrelation, and we're going to see how it relates to a concept called power spectral density. It turns out that autocorrelation and power spectral density tell us a lot about a random process. In fact, if we know one or the other, we can pretty much find just about everything we're interested in determining about most random processes. And it turns out that autocorrelation and power spectral density are related through a Fourier transform operation. Fourier transform of autocorrelation equals power spectral density. Turns out that autocorrelation, generally speaking, is easier to calculate, whereas power spectral density is more or less easier to measure. So we can get access to random process information either theoretically or experimentally. All right, enough talking. Let's go back just a bit and do a review of autocorrelation properties. Not so much a review of properties, but rather notation. All right, first of all, let's remind ourselves that autocorrelation really is a quantitative measure of the similarity of a random process to itself at some later or earlier instant in time. Let's write that down. Quantitative measure of the similarity of some random process x of t to itself at some earlier or later instant in time. Okay? That's what autocorrelation ultimately tells us. Some notation here. This is the notation for the ensemble averaged autocorrelation. Ensemble averaged autocorrelation. T1 and T2 are just two instances in time. Alright, T1 and T2 are just two distinct instances in time. So from an ensemble averaging perspective, what we do is we evaluate our random process at time T1, multiply that times random process x evaluated at time T2, multiply them, find the ensemble average. Alright, if x of t is at least wide sense stationary, then, and by the way, that's going to be us in most cases, then we can do this. We'll let time t1 equal just a general time parameter t, and we'll let t2 equal t plus tau, where tau is a shift parameter. Right? And my autocorrelation can be written as this. In this case, what I'm saying is that if my random process is at least wide sense stationary, then my autocorrelation doesn't depend upon the exact instances in time t1 and t2. Instead, it depends upon the separation between those two time instances. Okay? Let's call this equation 1. I'm going to need that in just a couple minutes. All right, let's go to the next page. I'm going to leave a little bit of room. If x of t is at least wide sense stationary, then we can start discussing time averages. All right, if a function is not stationary, meaning that its statistics change with time, then it makes no sense for us. It makes no sense for us to talk about time averaging. But if my random process is at least wide sense stationary, meaning that the statistics don't change with time, then we can start talking about time averaging. From a time averaged perspective, my autocorrelation looks like this. I've got these pointy brackets. Okay? And let's call this one equation 2. We'll need that in just a second. And from a time average perspective, the pointy brackets imply the following integral. Okay? This is my time averaged autocorrelation. Okay, it's my time averaged autocorrelation. And capital T here is just some temporal window over which we examine my random process, capital X. Strictly speaking, x of t, my random process x of t, does not have to be periodic, and so I would have to use this limiting operation and let my temporal window get arbitrarily large in order to calculate the autocorrelation. However, if x of t is periodic, then we drop the limit and let t equal the period. Okay? So if my random process is periodic, then we just drop the limit and let capital T equal the period of my random process. The reason being that the average of any periodic function over one period equals the average of that function over arbitrarily large number of periods. All right. Next is if x of t is at least wide sense ergodic. All right. That means that equation 1 and 2 above are equal. Meaning that I can find my autocorrelation in either by either time averaging or ensemble averaging. So my autocorrelation can either be written as a time average function, or it can be written as a statistical or ensemble average function. Okay? I'm happy to say that most of the time we are going to be dealing with at least wide sense ergodic random processes, so we will do our calculations in such a way as our life is made easiest. If it's easiest to do it statistically, we'll do it statistically. If it's easiest to do it through time averaging, we'll do it through time averaging. All right, and then the last property is if I evaluate my autocorrelation at 0, that is my mean squared value from an ensemble average perspective, and it equals the mean squared value also from a time average perspective if we're talking about at least a wide sense ergodic process, and this equals normalized power. All right, so the normalized power, remember normalized means 1 ohm load. So the normalized power in the random process is the mean squared value that can be found by evaluating my autocorrelation at 0 shift parameter. All right, so that's all I wanted to do in terms of for review. Now I want to dive a little bit deeper and talk about some more specific properties of autocorrelation. All right, we are going to exclusively consider at least wide sense stationary processes, and in most cases we'll consider wide sense ergodic processes. All right, so in all cases we're going to consider wide sense stationary processes. In most cases we will also consider wide sense ergodic processes. So from this point forward, if I say something is ergodic, I mean that to imply that I'm talking about at least a wide sense ergodic process. If I say something is stationary, I mean it's at least wide sense stationary. Just economy of words. If I say stationary, means wide sense stationary. If I say ergodic, means wide sense ergodic. All right, we're going to look at 5 properties. First property is that the autocorrelation evaluated for 0 shift is greater than the absolute value of the autocorrelation everywhere else. In other words, it's a maximum for 0 shift. If I plot autocorrelation versus shift parameter tau, when tau equals 0, I'm at the origin, I'm always going to have a peak value. All right? Second property. Turns out that autocorrelation is always even. All right? Autocorrelation is always even. Okay? If you ever see a function that is not even, it is not possible for it to be an autocorrelation result. Autocorrelation is always even. Third property, and I'll prove this to you a little bit later. Third property says that the limit as the absolute value of tau approaches infinity of my autocorrelation equals the square of the mean of x all right, and this is true, this property actually turns out it's true is if my random process is ergodic, meaning for us that it's at least wide sense ergodic. So this absolute value of tau means that tau approaches either plus or minus infinity. Okay? Remember that autocorrelation is an even function, so it'll take on the same value at plus infinity or minus infinity. If I have a random process that's ergodic, I can find the square of the mean by evaluating my autocorrelation at plus or minus infinity. Fourth property. If x of t is periodic, then the autocorrelation is periodic with same period. All right? If x of t is periodic, if I have a periodic random process, then my autocorrelation is also periodic with exactly the same period. Now what that would imply is that I'm going to have multiple peaks in my autocorrelation functions. In fact, I'll have periodic peaks in my autocorrelation function, but they will never be greater than the peak for zero shift. When I take any function and I compare it to itself with zero shift, my functions have to be most similar to themselves. All right. If I take a function and I shift it, if I have a periodic function rather, and I shift it by 1 period, 2 periods, 3 periods, arbitrarily large number of periods, it comes back in phase with itself. Excuse me, and becomes exactly similar to itself again. So I can have multiple peaks in a periodic autocorrelation, but those peaks will never be larger than the peak at the origin. And the fifth property is the Fourier transform of autocorrelation is power spectral density. All right. My curly F there indicates take the Fourier transform of what's inside of the curly brackets. In this case, I'm saying take the Fourier transform of autocorrelation, and I get, I'm going to introduce some new terminology here, the power spectral density, capital S, of omega. If I take the Fourier transform of a time domain function, I get something in the frequency domain. Capital S sub x is the notation we're going to use for power spectral density. We'll get there a little bit later. This has a special name. It's called the Wiener-Kinshine theorem. Okay, we'll have more to say about that in just a few minutes. So those are the 5 interesting properties of autocorrelation. We're going to spend some time looking at the 3rd and 5th properties. Let's look at the 3rd property first. Property 3. All right. Remember, we're talking about x of t is ergodic. At least wide sense ergodic. So my random process can be written as either it can be written as a time averaged function or an ensemble averaged function. can be written as a time average function or an ensemble average function. And so then we make an observation here. As tau approaches plus or minus infinity, then x of t becomes completely unrelated or uncorrelated to itself. All right. As my shift parameter approaches infinity, then x of t becomes completely uncorrelated to itself at some arbitrarily large time shift value later. In other words, what I'm doing today is going to be completely unrelated to what I'm doing 15, 20 years from now. Certainly would be completely unrelated to what I'm doing infinitely into the future or infinitely into the past. For this reason, we can say that as tau approaches plus or minus infinity, x of t and x of t plus tau become statistically independent. All right, if they're statistically independent, then my expectation of products becomes product of expectations. All right. If x of t and x of t plus tau become statistically independent, then my autocorrelation in the limit as absolute value of tau approaches infinity becomes product of expectations. Well, then this becomes I can drop the tau. If my random process is stationary, then the mean value of x of t is the same for all time. So I can drop the shift parameter tau. And by the way, we're talking about ergodic random processes, so ergodicity implies stationarity. So if my random process is ergodic, it's also stationary, I can drop the shift parameter tau. And then, of course, this is just the square of the mean, or the square of mu of x. Proved. Okay? So if x of t is ergodic, then I can find the mean, or at least the square of the mean, by evaluating the autocorrelation function at plus or minus infinity. We'll find that to be pretty handy. All right. Let's introduce the concept of power spectral density. I'm going to do before I start talking about power spectral density, however, I'm going to do a little bit of a review of a concept hopefully you've seen many times before, called Parseval's theorem. Parseval's theorem. Parseval's theorem applies for what we call energy signals. Energy signals are one for which the energy in the signal is not not less than or equal, strictly less than infinity. The energy has to be finite. All right? So Parseval's theorem says this. The energy in some function can be found by integrating in the time domain. If I have some function f of t, it might be a complex function. If I take its absolute value and square it, integrate over all possible time, I get the energy in that signal. I can also find it in the frequency domain. And this has units of joules. We're talking about energy. All right. I should also point out that we're really talking about normalized energy here. In other words, we're talking about a 1 ohm load. If f of t is a voltage or a current signal, the effective load that we're talking about here is 1 ohm. Okay, this is the energy that would be dissipated by f of t when it's dropped across a 1 ohm load. All right, so the overall units of energy are in joules. So this thing has to have units of joules per hertz, because that has units of hertz. All right? That has units of, my d omega term has units. Its units is hertz. So this thing this represents energy. If I integrate absolute value of capital F of omega, oh, by the way, I should point this out, that the Fourier transform of little f of t equals capital F of omega. They're Fourier transform. All right, if I Fourier transform little f of t, I get capital F of omega. All right, so my absolute value squared of f of omega represents energy spread across the frequency spectrum all right, capital F of omega quantity, or absolute value of capital F of omega squared represents the energy spread across the frequency spectrum of f of t. The reason being that if I integrate absolute value of capital F of omega squared for all frequencies, I get the total energy in my signal little f. This can therefore be written, or can be called, an energy spectral density. Okay, energy spectral density. So far this semester we've talked about probability densities. Probability density functions represent probability spread across the range of values that a random variable or random process can take on. If I take probability and I spread that across the range of values a random variable can take on, I get probability density. If I take energy and I spread that across a range of frequency variables or frequency parameters that a function contains, I get energy spectral density. Likewise, in a couple of minutes, we're going to talk about power spectral density, and that will represent power spread across the frequency spectrum of some function. That's what that means. Energy spectral density is energy spread across the frequency spectrum of a function. Power spectral density will be power spread across the spectrum of some function. All right. Power spectral density. Enough of an introduction. Power spectral density. That is supposed to be PSD. Power spectral density. All right. The following analysis is going to be valid for real ergodic random processes. But for simplicity, we're going to do the analysis assuming a real non-random function. Non-random. All right, so for simplicity's sake, I'm going to assume a real non-random function, but the result that we're going to come up with is true for real ergodic random processes. And oh, by the way, I state this without proof, that power spectral density as a concept simply does not exist unless we have at least a wide-sense stationary process. All right. For us to even begin the discussion of power spectral density, we have to start with the assumption that we're dealing with at least wide-sense stationary processes. I'm not going to get into that in any detail right now. If you're interested, let's talk about it. Okay. So we'll consider a signal f of t. And what we want to do is find the power spectral density of f of t. What we're going to do, power spectral density, I guess I should say this, f of t can be a power signal. Power signal means that the power is less than infinity. There's some other nuanced characteristics of power signals versus energy signals. Remember, power is the time rate of change of energy. An energy signal, for example, has to have finite energy. That would imply that it has no singularities at all, and it has to have finite duration. A power signal, on the other hand, simply has to have finite time-averaged power. I can have infinite duration signals, and I can have an occasional singularities and have finite power. Commonly, we as engineers are going to run into power signals more often than energy signals. Energy signals are a more complex class of signals. All right. Consider a signal f of t, which can be a power signal. First thing I'm going to do is I'm going to define a finite energy version of f of t. I'm going to define a finite energy version of f of t by truncation. this is what it's going to look like. Over some window, capital T, my truncated version of f is going to equal itself, f. And it's going to be 0 elsewhere. All right? So f of t could be an infinite duration signal, which means require infinite energy, but possibly finite power. I'm going to truncate that and examine it over a finite window, capital T. All right, let's move to the next page. The normalized power in f of t, remember, this implies that if f of t is a voltage or current signal, we're talking about a 1 ohm load. All right. The normalized power is just the mean squared value. All right. Normalized power is mean squared power, or RMS squared. RMS stands for root mean squared. But if I square a square root, I just get mean squared. All right? All right? Power is just the RMS squared version of f. The mean squared value is found this way. All right, that's how you find the mean square. I square it and I average it. If I square a function, I integrate over the window capital T and then divide by that window. That's how you average a function. Then I'm going to let the window get arbitrarily large. All right, so this is sort of the definition of time averaged mean squared. That's the definition of the time average mean squared. If I took the square root of that, I would get RMS. All right, this is then, when as t approaches infinity, I'm going to plug in my truncated version of f and let my limits on my integral go to plus or minus infinity. All right. Then I'm going to use Parseval's theorem. Okay. My integral, excluding the limit, my integral is an energy statement, so I can use Parseval's theorem. This is by application of Parseval's theorem. All right, that's by application of Parseval's theorem. And remember earlier I said we were going to talk about real non-random functions, f of t, but you'll notice that I've got an absolute value in here. Since the Fourier transform integral, when I take the Fourier transform of a function, that implies a complex integration process. So even if f of t is real, as we've said it was going to be for this analysis, f of omega is often complex. Thus, the need for the absolute values. Okay? One more step. Okay. And this, ladies and gentlemen, is all in watts. Okay? Let me go to the next page and rewrite my last equation and have something to say about it. Normalized power in a 1 ohm load can be written as this: 1 over 2 pi, integral from minus infinity to infinity of limit as t approaches infinity, absolute value squared of the Fourier transform of my truncated function, where the Fourier transform of my truncated temporal function equals capital F sub t of omega. All right. I can also write this as 1 over 2 pi integral minus infinity to infinity of a new function capital S sub f, capital S sub f of omega is limit as t approaches infinity, absolute value Fourier transform capital F sub t of omega squared divided by that, divided by capital T. This is power spectral density. And has units of watts per hertz. Okay? This thing right here, the omega has units of hertz. So the integran must have units of watts per hertz. And my power itself has units of watts. So what we have here, this function represents power spread across the frequency spectrum of little f. This is my relationship for power spectral density. Okay? I claim to you that in many cases power spectral density is challenging to calculate. Challenging is professor speak for it's hard. But relatively easy to measure. Often difficult to calculate, but it's relatively easy to measure. Okay, so one more thing before I move on and talk about this relatively easy to measure stuff. If you normalized power can be found several ways now. 1 over 2 pi times integral from minus infinity to infinity of S of omega. If you happen to have your power spectral density represented in what I call regular frequencies, not radian frequencies, then I can drop my 1 over 2 pi. Oops. Okay, omega is 2 pi nu, so omega is a radian frequency and nu is regular frequencies. I can also find power from evaluating the autocorrelation at 0, right? So I can find the normalized power in a function by several different methods. I can integrate power spectral density, or I can evaluate autocorrelation at 0. All right. Let's generalize this. This analysis was for real non-random processes, but let's talk about a random process. So let x of t be our random process. All right. Then that's that. Okay. All right. Now I have claimed to you that the that the power spectral density is relatively easy to measure. Finding the Fourier transform of a truncated version of the power of a random process, then finding its absolute value and taking the limit, even for simple random processes, is a relatively challenging thing to do. It's hard to calculate. But it turns out it's pretty easy to measure. As a matter of fact, many of you have already measured power spectral density, not even knowing it. So imagine if I've got, say, an oscilloscope, and remember I'm talking about a stationary random process, and I observe my random signal coming in over some, I change the time per division scale, and I know how many divisions I've got on my oscilloscope screen, so I know the observation window capital T, and perhaps this random process continues on outside of the window of observation. So what I would do is I observe my random process over some temporal window capital T, collect data, all right, and so this would be at least one sample function of my random process capital T. I collect digital data for t seconds, and then what I'm going to do is I can so I'm collecting data for capital T seconds. That's naturally the truncated version of my time domain signal. Take the Fourier transform, take the Fourier transform in MATLAB. You know, I can measure, I can digitize my signal over capital T seconds. That's naturally truncating my random process. I can feed that into MATLAB. MATLAB's happy to work with complex data. I can calculate the Fourier transform, square it, divide by the temporal window, and I can estimate my power spectral density. The estimate will get bigger as my time, as I change my time per division scale on my oscilloscope so that I'm seeing more and more and more of my random process, my estimate gets better. my estimate of my power spectral density will improve as the time over which I capture my sample function gets bigger and bigger and bigger. Okay, so I claim to you that calculating power spectral density is generally difficult, even for simple random processes, but it's not real difficult to measure in the lab. In fact, many of you have probably already done it. So, how does this all relate to autocorrelation? How does power spectral density relate to autocorrelation? That's the big question. Well, I've claimed that they're related to a Fourier transform operation. That's supposed to be a -1. So ideally, if I take the inverse Fourier transform of power spectral density, I ought to get autocorrelation. The inverse Fourier transform integral is this. All right, this is the definition, this is the defining integral for the inverse Fourier transform. Okay, so I'm not going to do the steps here. I'm not going to do the steps in this video lecture series. I have given you a handout, or I have provided for you a handout that shows all of the steps. As they say, the steps are quite straightforward, but it took me about a page to do the math. If I set up the inverse Fourier transform integral and proceed with all of the steps, I ultimately get the autocorrelation capital R sub x sub tau. Okay, so I'm not going to prove that in the video lecture. I've given you a handout to show you all of the steps. At the end of the day, the Fourier transform of autocorrelation equals the power spectral density. All right. Another way of writing this is that this is my notation. Autocorrelation and power spectral density form a Fourier transform pair. Autocorrelation and power spectral density form a Fourier transform pair. The fact that the Fourier transform of the autocorrelation equals the power spectral density is known as the Wiener-Kinshine theorem. All right. So for ergodic random processes, I can find the mean of my random process by evaluating the autocorrelation at plus or minus infinity. I can find the mean squared value of my random process by evaluating my autocorrelation at 0. Maybe my random process is something that's easier to measure than calculate. Well, I can go into the lab and I can measure power spectral density, find its inverse Fourier transform to get the autocorrelation, evaluate it at 0 and plus or minus infinity, get the mean squared value. From there, I can calculate standard deviation, variance, and all kinds of interesting things. It turns out that knowledge of either autocorrelation or power spectral density is sufficient in most cases to fully characterize the statistical behavior of most random processes that we as engineers are likely to encounter. Okay, let's do some examples. First one, random process that we've seen before. I've got a random process that's created by embedding a random variable inside of a time domain function. So this is capital theta is a random variable uniform on 0 to 2 pi. Okay? Previously we saw this. Previously we saw that. We have a periodic random process. We see that we end up with a periodic autocorrelation, and the period of the random process and the autocorrelation are identical. The power spectral density is then the power spectral density is a Fourier transform of the autocorrelation, and this is a squared over 2 times, I need a pi in here, times delta of omega minus omega naught plus delta omega plus omega naught. And I did this by looking up my Fourier transform pair in tables. I will make a table operational and functional Fourier transform table available to you. So you'll be the functions that we're going to consider will all be on that table. I'm not going to make you calculate Fourier transform integrals by hand. Okay, all the functions we're going to be interested in are going to be in the tables that I will provide to you. Here's one of them. I take a Fourier transform of a cosine function, I get 2 delta functions. All right. Well, the total power then is 1 over 2 pi, integral from minus infinity to infinity of my power spectral density. And that is a squared over 4, integral from minus infinity to infinity of delta omega minus omega naught plus delta omega plus omega naught d omega. Delta functions always have unit area, so this gives me a squared over 4 times 1 plus 1, or a squared over 2. And you'll notice that that equals, by examining this relationship right here, it equals my autocorrelation evaluated at 0. So if I integrate my power spectral density, I get back, or I get a result that's equal to evaluating my autocorrelation at 0. All right, let's do another example. Slightly more complicated and hopefully a little more interesting. This is going to be what I call the telegraph wave problem. All right. My random process is going to be capital X of t. And X of t takes on values plus a or minus a at each instant in time. All right, at each instant in time, my random process is either plus a or minus a. The probability that random process equals a equals the probability that random process x of t equals minus a, and that's a half. Half the time it's plus a, half the time it's minus a on average. Okay? A sample function might look something like this. If that's time t, this will be one sample function, and that'll be a plus a, and this will be minus a. Yeah, it'll look something like this. Okay, looks something like that. All right? It's going to switch back and forth between plus a and minus a. Now, another property is the number let k, little lowercase k be the number of polarity changes in a time interval tau. The number of polarity changes, k, in time interval tau obeys a Poisson distribution. And what that means is the probability that there are k switching events or polarity changes in time interval tau is some parameter alpha tau raised to the kth power e to the minus alpha tau divided by k factorial. Okay? K equals 0, 1, 2, 3, etc. K is an integer. All right? And alpha is a constant related to data rate or bit rate. And we'll see that a little bit later. All things being equal, as the data rate gets higher, alpha gets bigger. As the data rate gets smaller, alpha gets smaller. For now, it's just kind of a constant. All right. What we want to find is the autocorrelation and the power spectral density of the telegraph wave. Oops. Find the autocorrelation. This equals, you may have to give some thought to this, this equals the expectation of the product. When I take my random process x and multiply it times itself at some later or earlier instant in time, remember, my random process takes on either plus a or minus a values. So x times x of t plus tau can either take on values of plus a squared or minus a squared. So my expectation is a squared times the probability that x of t and x of t plus tau have the same sign, or same polarity, plus or minus, let's do it this way, a times minus a times the probability that x of t and x of t plus tau have opposite sign. Okay? And of course, a times minus a is minus a squared. Another way of writing this is that this is a squared times the probability of an even number of switching events. I'm going to get positive a squared plus a times plus a equals minus a times minus a equals a squared. And that's going to be the result if I have an even number of polarity changes over my time interval tau minus a squared times an odd number of polarity changes over tau seconds. Okay, so this equals a squared times the summation for k even of alpha tau to the kth power over k factorial e to the minus alpha tau minus a squared times summation I don't know what happened. Make that go away. I don't know what's going on, boys and girls. Well, let's just leave it there for now and go on. I don't have any idea what that is. Yeah, it went away. All right, where are we? Minus a squared times the summation of k odd alpha tau raised to the kth power over k factorial e to the minus alpha tau. Okay? I'm tacitly assuming at this point that tau is greater than or equal to 0. Okay? I'm tacitly assuming at this point that tau is greater than or equal to 0. All right. Now what I'm going to do is I'm going to notice that that negative 1 raised to the kth power equals plus 1 if k is even, and equals minus 1 if k is odd. Okay? Let's go to the next page and continue. I can combine the two parts of the equation on the bottom of the last page to get a squared times summation from k equals 0 to infinity negative alpha tau raised to the kth power over k factorial e to the minus alpha tau. All right. This piece right there is not a function of little k, so it can come outside of my summation. This is e to the minus alpha tau, a squared times summation k equals 0 to infinity negative alpha tau raised to the kth power over k factorial. Well, turns out that this equals a squared times e to the minus 2 alpha tau for tau greater than 0. The reason being, you've probably seen this in a calculus course somewhere, e to the x. E to the x can be written in terms of an infinite series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial and that equals summation from n equals 0 to infinity of x to the nth power over n factorial. So I've used this relationship there to get my result here. Okay? And then I make note that if tau is less than 0, we get the same result except a change of sign in the integral. In the exponent. And so the result that we're after, the autocorrelation for my telegraph waveform is a squared e to the minus 2 alpha times absolute value of my shift parameter. That's that. Okay? And the result looks something like this. All right. This is my autocorrelation. Okay, that is my autocorrelation for my telegraph wave. Assuming that A is 1 and, oops, I forgot something here. There's an A squared here. My figure here in the upper left-hand corner was plotted assuming that capital A is 1 and that my alpha parameter is 0.5. All right. Without proof, I'm not going to prove this for you. I'm not going to do this derivation. But the Fourier transform of my autocorrelation equals power spectral density, and that is plotted there. Okay? once again for capital A equals 1 and little alpha equal 0.5. Okay? You'll notice that the peak here is 1. And that equals A squared. All right. Over here, more generally, the autocorrelation evaluated at 0 would be A squared. All right. We're talking about an ergodic random process. So if I look at this autocorrelation at, we'll just assume that that's pretty close to plus infinity or minus infinity, what we'll see is that the mean is 0. And if we go back to the sample function that I sketched at the beginning of this example, you'll see that it's always either plus A or minus A, and it's half the time plus A and half the time minus A. On average, the sample functions have 0 mean. All right? They're centered at the origin. They're centered at 0 value. All right. The last thing I'll notice is that as alpha gets small, let me write this in a different color so we can see it. As alpha decreases, the autocorrelation gets wider and wider and wider. All right? As alpha approaches infinity, my autocorrelation approaches a delta function. All right? Remember, autocorrelation is a measure of the similarity of a function to itself at some earlier or later instant in time. So a function that is delta correlated, meaning that the autocorrelation takes on the delta function, means that it is completely dissimilar to itself at any earlier or later instant in time. For a telegraph wave, that's only going to be the case when I have an infinite data rate, an infinite number of changes in polarity for any given instant in time, for any time shift parameter. So from that we see that alpha is at least related to data rate. As data rate gets larger, alpha gets larger. As data rate gets smaller, alpha gets smaller. I don't know the functional form that relates alpha to data rate. I can just simply say that alpha seems to be related to data rate. Data rate increases, bigger alpha. Data rate decreases, smaller alpha. Okay. That, ladies and gentlemen, is all I have for the day. As usual, if you have any questions, please contact me at your earliest convenience, and I will be happy to answer any and all questions as fully as I am able. Have a nice day. Bye-bye.